Hello everyone, my name is Alana Jurgensen and today I will talk about manifold-aware denoising score matching. And this is joint work with Alvaro Pratt, James Kewen and E.Y. Tay. So let me start with a reminder or introduction to diffusion models, the score-based approach. So as with all generated models, our goal is to generate samples from some data distribution. And one way of doing that in this context is to use stochastic differential equations. Basically, this allows us to transform from our data distribution to a normal distribution and backwards from a normal distribution to the data distribution. And the nice thing about this is that it allows us to sample from a normal distribution, which is something that we know how to do, and get from a sample that is distributed according to a normal distribution to a data sample. The catch is that we need, in order to do this reverse process from a normal distribution to the data distribution, we need this score function. And this in general is intractable. So what we do typically is we use a neural network to approximate this. So what's the problem with this? So the problem is that vanilla diffusion, denoising score matching specifically, actually struggles to learn certain manifolds from the data alone. So it's not basically aware of where the data resides, what the manifold is. So in this case, the manifold is a unit circle. And so vanilla approach should not be expected to easily identify this, if not implicitly from the data set. Okay, so the only way it can learn it is implicitly from the provided data set. And you can imagine that if there isn't enough data, it might not be able to tell what the actual manifold looks like. Okay, so why is this important? So a lot of actual real life data that is of interest for us, like climate data, robotics, drug design, these are all supported on unique manifolds, like spheres, for example, like what we just saw now. And so the vanilla diffusion has to resolve to learning this structure implicitly from the data. So for example, we have Earth data on a two-sphere rotation data, as I mentioned, which can be represented in 4 dimensions on a three-sphere. So we can't actually illustrate it because it's in 4 dimensions, but what I can say is that it's important for robotics and for drug design, and I can sort of illustrate that for you because here we have an illustration of a drug that's binding to a breast cancer receptor after it correctly rotates in order to do this binding successfully. So how can we solve this problem? So previous approaches typically either define a diffusion process on the manifold, so for example, on the sphere or on the unit circle, or locally convert the manifold to Euclidean coordinates, a flat geometry where standard diffusion tools apply, and this requires multiple local sort of mappings for this to work. So this can be very costly during training and or sampling. Both of these approaches can be. And so the question is, can we instead retain the simplicity of the vanilla approach, the denoising score matching, but inform it somehow of the manifold? So let's see how we might be able to do that. So in some important cases, we know what the manifold is, like the two-sphere or the three-sphere. And so the question is, can we use this to somehow inform diffusion in these cases? So let's see how we might do that by investigating a simple case. So here we have the unit circle as the support manifold. And now we can see some sort of data set that we have on it. So these are samples from a data, and it kind of looks like a normal distribution on the circle. It sort of gets thinner around the corners. So we actually need to learn the score in order to be able to generate samples from this distribution. So we need this little fellow here that we typically find very difficult to get. So if this were actually a simple distribution, maybe we could actually derive this score analytically. So specifically, if this was a uniform distribution looking like this, then we can actually derive the score analytically. So let's call this the base score and denote it by S base. So the question is, how is this actually useful? Because what we wanted was this distribution, not the uniform distribution. So here is our suggestion. This is the key slide, basically. What we are suggesting is that if you have a base score analytically, then just learn the difference. So the thing is, you should really, what we're offering is to really find a distribution for which you can actually derive the analytical base score, and then learn the difference between the score and this actual base score. So this is actually a decomposition of the score function into the difference and the base score. And so we're suggesting to learn this delta. So here is another example. Basically, we have M, the support manifold here is the two-sphere, and this is the uniform distribution or samples from the uniform distribution, which we generated actually using the base score. So we got the base score analytically for this case. And in fact, in the paper, we actually derive the base score for all n spheres. So if you've got data residing on an n sphere, we have got you covered. And this includes the three sphere for rotation data, which we saw is really important for robotics and medicine. We also have this for the finite discrete set of points, which you might be wondering, why is that interesting? And actually, it is interesting in the context of bioinformatics and language models, where we have discrete distributions. So why would we expect that learning the difference would be helpful? So intuitively, what we're doing is we're adding valuable information about the manifold implicitly through the base score, but we're adding it to the problem. So one would expect this to reduce the burden of solving this problem. The second reason is that the score function, which includes S and S base, they are both score functions, increase as the noise gets smaller. So maybe the difference between them might actually have improved scaling. And in fact, in the paper, we do prove this for the discrete case, where we can see that the difference actually tends to zero as the noise gets smaller. And we even illustrate this as well. So here you can see that the magnitude of the score function, which is the target of the vanilla denoising score matching approach, actually explodes as sigma goes to zero, whereas the target for our approach is stable and does not explode to zero, to infinity. So how do we parameterize this, and what is our loss function? So it's very simple. As I said, we have a neural network to learn the difference. And so if the vanilla approach learned the score, so there was a neural network for the score function and the learning target was this, then our learning target becomes the same thing minus the base score. So it's the difference. And then again, we have a neural network for the difference. So recall the problem that we had where the vanilla diffusion struggled to learn the manifold and the distribution on it from the data alone implicitly. And so in our case, what we can see is that MAD can actually successfully reach the manifold structure as well. Okay, so let's look at some results. So we ran some controlled experiments for Earth data, SO3 synthetic data, and discrete data, meaning we have the same training and evaluation samples, number of steps, architecture as much as possible, and batch size. And what we did was we used a metric for manifolds that is sample-based, and that is the maximum mean discrepancy, as in previous work as well. So for Earth, for example, we can see that we have improved MMD, so lower MMD is better compared to on manifold methods, and similar MMD compared to DSM, while capturing actually sharper distributional detail. So we have sharper distributional detail compared to DSM when this is the actual data. For rotation data, so for example, our data set is a mixture of wrapped normal distributions with k components. So here we can see k equals 64. And we have here improved sample time. We can see the sample time compared to the methods that have the best MMD. So you can see the top method is actually underperforming the other methods. And so here you can see that MAD has very good sample time compared to one of the best methods here. And actually that MAD might have an advantage with more complex distributions, because we can see that although RSGM is performing really well for case 16. When you sort of increase the number of components, so you increase the complexity of the distribution, you actually can see that the other methods, including MAD, is actually catching up very quickly. And again, we can see sharper distributional detail compared to DSM, and you need to sort of look between the components to see why. But you can see that here with DSM, there's less of a separation between the components. For example, here, here, here as well, and here. And then in these same regions, you can see that there's actually a much better separation with MAD, and here as well, actually. Okay, so we can also see improved training speed with both MAD and DSM when with DSM, so this is MAD, sorry, and this is DSM, and with MAD we can actually see a much earlier convergence, which implies that it has less to learn. And in the paper, you can find more experiments on a conditional version for SO3 with object rotations, more complicated scenario where we see improved performance for some of the shapes and better manifold proximity compared to DSM. And finally, we also have the discrete set. So here we can see two types of data sets that we sort of experimented with. So we have the uniform, it's like a discrete unit circle, and here we have the skewed data set. And what we can see is that MAD really matches the actual data distribution very well, whereas DSM really struggles. Okay, so a few conclusions and limitations. So MAD decomposes the score to account for the manifold via a base score. And we derive the base score analytically for several important cases. And the results show that MAD can actually improve convergence speed, distributional detail, and can compete against other methods, especially when the dataset is complex and when the dataset is sparser or smaller, like in the Earth experiments and complexity we saw with K64 in the SO3 case. The downside is that MAD requires an analytical score. So we have derived analytical scores for the important cases we discussed, but if others are needed, it is not entirely clear how easy it would be to get those, and perhaps approximations would be something to go for in those cases. So for future work, what we're looking to investigate is higher dimensions where we believe the problem of learning the manifold implicitly from the data is likely going to be exacerbated. You can imagine that with less data, it would be even less clear, or rather, when there is higher dimension, you'd need a lot more data to make it clearer what the manifold is for the model implicitly. So we believe MAD will have an even stronger advantage there, and also the discrete case, experimenting with domain-specific cases as well. Okay, thank you for listening.